Good morning. We are headed into another chapter on circuits. So chapter 25, we took a look at current and resistors. Chapter 24, we had looked at capacitors. And now we're ready to look at some more detailed types of circuitry. So let's do that. Now we're going to say this is DC circuits. DC circuits means that we're operating off something that is a DC voltage supply, and that would be something like a battery. So something where the voltage is being maintained at a fixed value. All right, so the first thing we want to talk about very briefly, not a super important topic for us, but an electric battery produces a voltage. The voltages are sometimes referred to as an EMF. It stands for electromotive force, and now electromotive force sounds kind of outdated, but we do still use the abbreviation of EMF. So the battery's voltage source is almost constant, but a battery has a certain amount of internal resistance. And so that says that the voltage at the terminals on the battery is determined by the EMF, kind of the, well, for a battery, let's think of a chemical reaction. So for a battery, it's running a particular chemical reaction, and that chemical reaction, as long as there is adequate reagent available, and the reagent can easily find the other reagent, as long as the reagents are in a location where they can easily come into contact, we can maintain a certain voltage as that chemical reaction takes place. Now what happens is, within the battery itself, the way that it's built, there could be different amounts of resistance that are actually in the battery casing and such. And so what happens is, we can actually end up with a voltage, the available voltage in a battery might not be the entire EMF of the chemical reaction. So if we're looking at something in detail, then here's a picture of a battery, and the terminal voltage is kind of what we're interested in. If we connect to the terminal voltage, we're going to get not the full EMF of the chemical reaction itself, but it's going to be reduced because of the internal resistance. Now, if you notice, the way that we're thinking about the internal resistance then is as the current increases, the terminal voltage will go down. So it could be that if my battery, if the reagents are depleted, for example, I could find that there is so much internal resistance now that the terminal voltage has dropped significantly. Maybe my car won't start because the battery terminal voltage has dropped below a certain value. Now I could get out a voltmeter and I could attach a voltmeter, and when the voltmeter is attached, there's really not any current going through here. So the voltmeter will tell me that, hey, the EMF is still here. I still have 12 volts of EMF. And then I go and try and start my car, but it still won't start. And that's because what I need to do is take the voltmeter, attach it, keep it attached, and then try starting the car. So when the car is started, you're going to start to draw a lot of current. So the value of the current goes up, and I'll lose more and more voltage because of the internal resistance. So the terminal voltage will drop significantly in that case, and maybe my car just isn't going to start because of that. So here's an example. We've got a battery right here. Oh look, it's kind of like a car battery. It's 12 volts. And built into that battery is a half ohm of internal resistance. So that's not bad. It's only a half ohm of internal resistance. How much of an effect could that have? And then over here is 65 ohms of something in the car that I want to start. Let's see what they tell us in the problem. A 65 ohm resistance. Now, it sounds like too much resistance. I don't think it's like a headlight or something, but some kind of a device in the car has a 64 ohm resistance to it. And the internal resistance is 0.5 ohms. What would be the current in the circuit? What's the terminal voltage on the battery? So let's go in and see if we can answer all these questions. So notice that what I have now, and I guess I kind of, I didn't go through and calculate this one. Okay, so this is not one of the ones that I did a solution to. So again, you can check with the textbook and see what values they came up with. I should go back and add that one in. So occasionally I'm running into those. Let's take a look and see what happens when we have a battery and we do have more than one resistor set up. And this is actually going to tell us how to go back and solve that problem we just kind of skipped. So if I've got 3 resistors set up, what I can say is that the voltage of the battery is going to get divided up by those 3 resistors. Let's go back and take a look at the setup here. So there's going to be a current going through the circuit. The circuit so far is simple enough that it just consists of one loop. This circuit only has one loop to it, and that means that everywhere in the circuit I'm going to have the same current. And as we've talked about before, when I close the switch on this circuit, I am simultaneously going to have current everywhere. So it's not like I have to wait for a current to go through resistor 1 until it gets to... The current is everywhere simultaneously because I have electrons all through the wiring. And so as soon as I close the circuit, I've got current, current, current here, all at the same time, and that current will have the same value everywhere. So I1 matches I2, matches I3, matches the current going through the battery. They all match. Now, the resistances don't necessarily. And that's as if I get out my voltmeter and I measure the voltage here, and I measure the voltage here, and I measure the voltage here. So I'm measuring the voltage across each one of the resistors. And each one of the resistors will provide a voltage drop. And so if I think of the battery as, I don't know, 12 volts or whatever, some of that voltage will be here, some will be here, and some will be here. So V1 plus V2 plus V3 are going to add up to total V. Similarly, current 1, well, not similarly, differently, current 1 will equal current 2 will equal current 3. Let's write those equations down and see what they tell us. So the total voltage is equal to V1 plus V2 plus V3. That's going to equal R1 times I plus R2 times I plus R3 times I. This is an example of resistors in series. Now we looked at the same kind of situation with capacitors. We looked at capacitors actually in parallel at first, and then later we looked at capacitors in series. With resistors we tend to start in series because that's the easier way to think about resistances. If I put resistors all together, it kind of feels like the resistances are just going to add together, right? In order for this current to flow, the current, if I think of the current everywhere, it's got to deal with resistance 3, 2, and 1. So let's see if that's really the case, if our intuition is correct. And the mathematics says, yeah, that's what it's going to work out to be. Because what I can do here is I can factor out a common factor of I, and then I'll factor out the R1 plus R2 and R3, and R1 plus R2 plus R3 together is going to equal R equivalent. So I can take all 3 of those resistors and just combine them into one equivalent resistance. Okay, and again, we're looking at resistors in series and parallel, but we're going to start off looking at series resistors. So now instead of having those 3 resistors lined up, I have one resistor that I've replaced it with, and it's creating the equivalent effect. What would parallel look like? Well, parallel in resistors looks like parallel in capacitors in that I follow the circuit to some point, and then I see these parallel paths. So I can take path 1 or path 2 or path 3. In series, I had to go through all 3 of them. But in parallel, I'm only allowed to follow one of those paths. So that means that I'll have a certain amount of current here, a certain amount of current here and here. Each path will have a different current, I1, I2, and I3. Now, if all the resistances are the same, then I1 and I2 and I3 will match. But in general, all of the resistors are attached in a way where they're getting the full voltage of the battery. This is a nice picture, a nice diagram of what's going on here. And so each of the resistors is getting, in some sense, they're connected directly to that full voltage of the battery. In fact, they are. And so V1 matches V2, matches V3, and they're all equal to the battery. Now there's an R equivalent for this too, and let's take a look and see what that would look like. In this situation where we are running in parallel, it's the currents that add together to get a total current, and then I'm going to define R equivalent such that the total current is V over the R equivalent. And for resistor 1, that's going to be the voltage divided by R1. All of the individual resistors are getting the same voltage. Now in this formula, I can factor out the V's, and when I factor out V's, they're going to get replaced with 1s, and that's going to be the formula for equivalent resistance in our parallel circuit. Okay, so the formulas for adding resistances in series and parallel look very similar to the formulas we derived for capacitors, except series and parallel seem to be switched. With capacitors, it's when the capacitors are in parallel that they just add together. And in series, it's the reciprocals that add. With resistors, that situation is opposite. It's when they're in parallel that we add the inverses together. Okay, so keep that in mind. So here is here's an analogy that they want to use. They're saying that when we have parallel resistors, the water can actually come out through more than one stream. So I'm going to have current going through one of the branches, and I'll have current going through the other branch, and in our case we had 3 of these. And what's happening is now I'm going to have currents that are, the overall current is going to increase. Every time I provide an additional path, that's going to allow more current to go through the circuit. Now here's a situation where I've got 2 resistors here. Again, it looks like a car battery, and here are my headlights. These headlights have been attached in series, and these headlights have been attached in parallel. Now, the problem with connecting these headlamps or these headlights in series is, notice that if this one goes out, for some reason the filament breaks, this one goes off too. So if I've attached things just simply in series, then when one of those goes out, the other one is going to stop working. In parallel, that's not the case. So in parallel, if this branch shuts down, it doesn't affect this branch. This branch is independent of that light bulb. So one of the light bulbs goes out, but the remaining light bulb is still going to work. Now it says here that these light bulbs are identical. If we were actually going to design this to operate in series, we would want to change the resistances here. Each one of these light bulbs has a certain amount of resistance to it. And so in this case, I'm going to have a total resistance of R plus R. I'm going to have a resistance of 2 times R. If each one of these is 100 ohms, well, combined, that's going to be 200 ohms of resistance. And that's going to reduce the current. What about in this case? Well, in this case, I'm going to end up with, if this is 100 ohms and this is 100 ohms, The formulas that we just came up with for adding things in parallel, that would be 1 over 100 plus 1 over 100 would be 1 over 50. We actually reduce the overall resistance when we add things in parallel. So the bottom line here is these lights would be getting only half of the voltage. They would have only half the current going through. So these would only be 1/4 as bright if they're the same resistance. Okay, so a factor of 4 between two bulbs being put in parallel or being put in series. Okay, here's another example. Here's one we can plug some numbers into. I've got a 120 volt source. I have two resistors here that are in, what does that look like? They look like they're parallel. It's I take this path or I take this path. These are in series. So this is going to give me more overall resistance. That's going to give me lower overall resistance. Let's run the numbers and see what we find. And then this circuit somehow is missing a piece right there. Maybe that was a switch that got dropped out or something. Not sure about that one. All right, here's what this looks like. First of all, notice that these bulbs were rated in terms of watts. Well, we can't rate the bulbs in terms of watts. We got to rate the bulbs in terms of ohms. The fundamental property of these light bulbs is a certain amount of resistance. And so the first thing I got to do is convert these watts into how many ohms is this resistor and how many ohms is this one. So let's do that. Okay, yeah, I think we've got enough information we can go along with this. So let's say the intention here was to operate this. I gotta go back and double check here. Oh, here we go. Yeah. Got it. Okay. Yeah, I was looking for this. Somehow I missed it before. These 100-watt bulbs and the 60-watt bulbs are designed for 120 volts. So they're designed to be attached in this parallel fashion. They're actually not designed for that circuit. They're designed for this one. So that's going to be important for us when we go in to calculate how much resistance each one has. Now what we can say is that one of the formulas we have for the power of a resistor, the rate at which energy is being used in a resistor, is V squared over R. So I'm going to use that formula and solve for R. R then is equal to V squared over the power. Now the first light bulb it said was rated, or maybe one of the light bulbs was rated at 60 watts and 120 volts. I can use those to find out what the actual resistance of that light bulb is. And it says the one listed as 60 watts is a 240 ohm bulb. That's the actual property of that light bulb. So I've got the resistance of this light bulb figured out. The other light bulb says it will be 100 watts if we plug it into 120 volts. Using the same formula, I find that this bulb has 144 ohms of resistance. So I've got two light bulbs, and now one of them, I know the resistances. So this one's at 240 ohms, the other one's at 144. So I'm going to redraw my circuit and kind of start the problem over. I have a 240 ohm bulb here. That's the one rated at 60 watts. And I have a 144 ohm bulb here. And I'm operating off of AC. So we'll say that this is a 120 volt outlet or a 120 volt source that I've attached my light fixtures to. And this would be in parallel, and this is what it would look like in series. Now, that was the first item to come up with. And again, I guess it's just conceptual. So what we've done is come up with the resistances for these two light bulbs. And now I can go in and calculate current 1 and current 2 as voltage divided by that resistance. okay, for each one of those. Okay, when I put these two in series, I'm going to end up with more resistance, and I'm going to end up with a reduced current. The current will be the same through both of these, and I'm going to have lower currents and lower voltages in the lower picture. Okay, here's another example, and in this one what we've got is we've got our 12-volt battery that we're taking a look at. Here's a 400 ohm resistor, and then here is the 500 ohm and 700 set of resistors, and these guys are in parallel. So how would I find out how much current is running through each of these resistors? So let's see if we can come up with that. So let's look at a little more detail here. So what I'm going to do is I'm going to start off with this circuit, and initially what I notice is that R1 and R2 are in parallel. So R1 and R2 can be combined in parallel. None of the other resistors are in direct parallel or series, so I'm specifically going to start with R1 and R2. I'm going to use the formula that we have derived for resistors in parallel, and it tells me using that the overall resistance here is 292 ohms. Now, once I have R12 figured out, I've collapsed those two resistors. They now can be treated as one equivalent resistor, and I can take the resistance R12, and now that can be combined in series with R3. So I'll take the 292 number and combine it with the 400 ohms, and that will give me a combined resistance 1, 2, 3 that is 692 ohms. The current then that I have going through this entire circuit, the current coming through the battery, will be the voltage of the battery divided by the combined resistance of the entire circuit. And we've shown that the entire resistance of the combined circuit is 692 ohms. Putting that in says that current 3 is going to be 0.0173 amps. That's not much current. Let's see, how many volts did we have? Oh, there you go. So we only had 12 volts to work from, and the resistances we put in were just hundreds of ohms, and as a result, we're only getting 17.3 milliamps. So the currents are pretty low. That's fine. Now what we can do is we've solved for current 3. Current 3 applies to this branch of the circuit. So that is the branch that runs through the battery. It's the branch that runs through resistor 3. But when I get to resistor 1 and 2, I3 separates into two sections, two separate currents. Now what I do know is that I1 and I2 combined, the combined flow rate of I1 and I2 matches the flow rate of I3. I can think of it as I3 approaches, junction, separates into I1 and I2, and then converges back together at the junction on the other side. And so I'm looking to make sure that that matches up. That's going to be a requirement. When I get to my final results, that's going to be a set of numbers that I'm looking at to check and see if everything has operated correctly. So this is the current. Now the voltage that I have across that resistor, I'm going to focus on this resistor for just a minute, is going to be given by V3 is going to be I3 times R3, and that's going to be 6.94 volts. So 6.94 volts is across resistor 3. How much is left for resistor 1, 2? So there's a voltage here, there's a voltage here, and resistor 1, 2, the voltage 1, 2, is going to be the total 12 volts minus the 6.9 volts. That leaves us with 5.06. Now, that voltage that we solved for, V12, applies to resistor 1 and resistor 2. 1 and 2 are in parallel, and they both have been, they're both experiencing the same voltage. So I now know all the voltages. V3 is 6.94 volts. V1 and V2 are 5.06. That's going to allow me to calculate the current through resistor 1 and resistor 2. So putting in V1 divided by R1. See how I'm becoming specific for each device. Each device, potentially, is going to have its own value of voltage, its own value of current, and its own value of resistance. Maybe some of those numbers match another device in the circuit, but I got to think in terms of each device either individually or in one of these equivalent resistances. And now I'm down to the individual level. So V1 divided by R1 gives me 10.1 milliamps, and V2 divided by R2 gives me 7.2. Now, if we've done everything correctly, it should be that I1 plus I2 is equal to I3. That's what my diagram shows. So let's ask if that's accurate. Well, 10 plus 1, 10.1 plus 7.2 does add up to 17.3. So we're looking pretty good with that. That looks like it actually did work. So that gives us some confidence that we've done the problem correctly. Now at the end of a problem, I always like to go back and calculate the power. I like to ask these questions on midterms too. So how much energy is being used, at what rate is energy being thermalized in each one of the resistors? So each one of the resistors is in the process of converting electrical energy to thermal energy, and so I can do P1, P2, and P3 by multiplying V1 and I1, V2 and I2, V3 and I3. I can, again, look at each of those three devices individually. This is at 51.1 milliwatts, 36.4 milliwatts, and 120.1 milliwatts. Now, the rate at which energy is going into the resistors should match the rate at which energy is being provided from the battery. And for the battery, I can take the 12 volts and divide by the current. The current going through the battery is 17.3 milliamps. So if I take the 12 volts times the 17.3 milliamps, that will tell me the rate at which energy is being provided by the battery. And that number, what's 12 times 17 is 132. It's plausible. I mean, I guess we should go in and check. But, you know, check that number. If I take 17.3 milliamps, multiply by the 12 volts, check and see that that number adds up to the total rate at which energy is becoming thermal in the combined three resistors. Okay, it should work. If we've done everything correctly, that's something that should show up. All right, the circuits get more complicated. And so here is, here's another example, analyzing a circuit. And what we have in this one is, I've got a 9-volt battery. I've got a little bit of resistance here. It seems like this is a internal resistance that they're referring to. I've got 5 ohms here. You can see what we've got. How are we going to simplify this circuit? And the idea is this. The idea is, if possible, there's no guarantee this is possible for a given circuit, but if we're fortunate, we will be able to start combining resistors. And the question we ask, is there anything that is immediately in this circuit? Are there any resistors that are in series with each other? And there aren't. Okay? Any resistors that were in series, you would have to go through, if I go through one of those resistors, I have to go through the other one. And that's not happening, right? These resistors are all kind of ended. Oh, here's one. The 5 ohms here and the 0.5 ohms, those could actually be combined. So that could be combined into one circuit, but we're not going to go to that one first. So what the outline is showing is, let's start out here in the farther regions of the circuit. I'm going to combine the 8 and the 4 together. Now remember, I got to take 1 over 8 plus 1 over 4. That's going to give me, what, 3/8, and I got to take the inverse, 8/3. So this is going to be like 2.667. So 2.7 ohms comes from combining these two. Now I would tend to label these as R1 and R2, and then this I would call R12. I want some kind of notation where it's easy for me to keep track of all the original resistors and then all of the resistor combinations that we've come up with. So, moving on, once I've combined this into one resistor, then I can combine these two in series. So I'll call this resistor 1 and 2, combine that, and then combine resistor 3. Now I have resistor 1, 2, 3 here, and they're saying, I took the 6 and the 2.7, combined those together and got 8.7. When I do that, then I can combine the 10 and the 8.7, but for this I got to go back and use parallel. So what's happening here is combination in parallel allows these combined in series, allows these to be combined in parallel, and then I got a circuit like this where everything is in series. So I can take the 4.8, the 5, the 0.5, add those all together. That will give me the total combined equivalent resistance for that circuit. So again, let me suggest, this is a good example to work through. Go through, step through this from one picture to the next, label all your resistors, and decide how much resistance you've got. Check their numbers and see if they're getting the right numbers for the equivalent resistance. All right, here is, here's another circuit, right? Here's a battery. Surprisingly, this battery is 80 volts. I'm not familiar with any 80 volt batteries, but if you string a bunch of batteries together in series, you could create an 80 volt battery. That would take like 6.5 car batteries, something like that. Connected all in series would be getting pretty close to 80 volts. Here's a little bit of internal resistance. Here's some resistance here. So you can see that we've got, well, not just the one battery, but we have two batteries. So for this, what we can do is set up a series of different currents. So I've got current 1, I've got current 2, I've got current 3 going through the different branches. And then for each one of the branches, I can identify how many volts I have, and I can identify how much resistance I've got. So this is an example of a more complicated circuit that we would have to solve using loops. And so I'm going to say this is a more complicated circuit, and I'm just going to set it aside for right now. And then I'm going to come back with a different, more general example where we can solve this. So this is how it works. What we can do is I can take, in fact, let's just take a look at that right now. I'm going to say that here is a circuit. I've got two batteries, V1 and V2. Along the path of each one of those batteries, I have some resistance. So I'll call this branch, the combined resistance along this branch is R1, combined resistance along this branch is R2, and then the combined resistance along this branch, which has no battery, is R3. So what I can do now is from this diagram and that diagram, I can start putting together what are called voltage loop equations and current equations. So let's take a look at, so this is the structure of my circuit. This is kind of the skeleton. And what I'm going to do is this. I'm going to define some currents. I'm going to say this branch on the left, I'm going to say that current is I1. And the branch down the middle, I'm going to call that current I2. And then this branch that has no battery, I'm going to call that I3. And if I look at these junction points, I can see that I1 and I2 come together to create I3. And then at this junction, I3 separates back out again into I1 and I2. So that says that I3 is equal to I1 plus I2, and that gives me a junction equation which relates currents. So I have an equation in terms of the three currents, and that gives me one equation. I have three unknowns. I only have one equation so far. So I got to find some other equations. Now the other equations are going to come from voltage loop equations, and let's go back and see what that looks like. So here is my 12-volt battery, and if I have a 12-volt battery here, what I can do is go around the circuit and say, all right, if point D is at 0 volts, then by the time I'm at point E, the battery has raised my voltage. That's a voltage boost, and the battery has raised my voltage by 12 volts. So the battery is providing a voltage boost of 12. And then all of the other resistors are going to provide a voltage drop. So let's see, I went from point E to A. I didn't go through any devices. And so the voltage stayed the same. I'm going to label that as still at 12 volts. But then I'm going to go through the first resistor to point B, and then I'm going to go through another resistor. Now what I know is that by the time I get to point C, I am back to 0 volts. So I'm going to get 12 volts of boost from the battery. I'm going to get 12 volts of drop from the two resistors. And what I can do is set those equal to each other. So that's what I'm going to do in this equation. I'm going to say if I add up all the voltage boosts in a loop, I can set those equal to the voltage drops. Now, what loops could we imagine using? Let's see. There is a loop that goes all the way around the outside. There's another loop that goes through the middle and goes around the outside. There's also a loop that goes around the left side and back through the middle. Any of those loops would work. Now, the way I'm going to decide which loops to use, I want to use whatever loops make the problem the easiest for me. You know, I'm just looking at this circuit and thinking, I'm guessing because the batteries are in these two branches, that the batteries will have the current going in this direction for for branch 1 and this direction for branch 2. So I'm thinking that's why I've chosen those directions. And then when those two currents come together, they'll return back through branch 3. So what I've tried to do is predict the direction that the currents will be traveling. What happens if I've guessed wrong? And it turns out that I'm okay. As long as I consistently set up all the equations, if one of these currents is reversed from what I've guessed, it will just show up as a negative value. So once I've solved for all the currents, a positive value tells me that, yes, it's in the direction that I guessed it was in. A negative value just says it's in the direction opposite to the direction that I guessed. So that'll work. So that's my reasoning. I'm trying to pick the easiest current equations and the easiest voltage loop equations. If I want to really challenge myself, I could try picking whatever directions I want and picking whichever voltage loop equations. And if I'm able to keep track of all the plus and minus signs switching back and forth, I'll be fine. Okay? Again, if I can do the problem and set it up consistently, it'll work. All right, now if I look at loop number 1, remember loop number 1 goes all the way around the outside. I've got a voltage boost of V1. I have a voltage drop of R1 times I1. So R1 has I1 passing through it. That's the voltage drop for that resistor. I also have a voltage drop at resistor 3, and resistor 3 has current 3 passing through it. Now another thing you'll notice in setting up these equations is I've set them up with subscripts where all the subscripts match. So I'm trying to make the algebra as simple to follow as possible. That's for myself, and for you guys too, but it's for myself to try and minimize the chance that I mix something up. And so I'm looking for patterns here. R1, I1, that's the voltage drop for resistor 1. R3, I3, that's the voltage drop for resistor 2. Now I can do another loop equation. The other one I decided to use was through the middle and then back through the outside. That loop contains one battery also. This time it's battery 2, which provides voltage V2. And this loop has 2 voltage drops. It has a voltage drop through resistor 2, and it has a voltage drop through resistor 3. Here is the voltage drop in resistor 2, and here is the voltage drop in resistor 3. Now what I'm trying to do is, I've got 3 equations now, 3 unknowns. I'm trying to combine the equations so I can start eliminating some of the unknowns. And so the first thing I'm going to do is, I'm going to use this equation to eliminate current 3. So see where it says current 3? I'm going to rewrite this equation and replace current 3 with I1 plus I2. And that happens not only in loop 1, but also in loop 2. So both of those occurrences of current 3 are getting replaced by I1 plus I2. I've removed I3 from my equations. I've also used that equation. So now I'm down to these 2 equations. V1 equals all this stuff at the end. V2 equals all the stuff at the end of this one. So 2 equations, 2 unknowns. That's better than 3 equations, 3 unknowns. And then what I'm going to do is I'm going to take equation 1. What I'm going to try and do next is eliminate I2. Now I2 has a coefficient of R3, and I2 here has a coefficient of R2 plus R3. If I multiply this equation all the way across by R2 plus R3, and I multiply this lower equation by just R3, that will give me the same coefficients in front of the I2s, and then I can subtract the 2 equations. So that's kind of my algebraic strategy that I'm going to try and follow here, is that I'm going to get those 2 equations to cancel out with each other. So that's what I've done. I've multiplied the top equation by R2 plus R3, and I've multiplied the lower equation by R3, and all this stuff is what I've ended up with. And if I notice, sure enough, these last terms that include I2, they match. That was my intention. And now I'm going to subtract the lower equation from the upper one. If I subtract the terms on the left sides of the equations, that's R2 plus R3 times V1 minus R3 times V2. That's in terms of the voltage boosts. And then on this side, the I2s drop out. So I'm left with R2, R3 times R1 plus R3, R3, R3. So I've subtracted that off by some, well, I'm not going to say it's a, yeah, maybe it's a miracle. This expression, when I multiply it out, I have an R3, R3 here, which is subtracted here. And so the R3, R3 term drops out. What I'm left with is R1, R2, R2, R3, and R3, R1 times current 1. All right, I am ready to write down the answer. I1 then, is going to be given by R2 plus R3 times V1 minus R3 times V2 divided by R1 R2 plus R2 R3 plus R3 R1. Now this is a lot of algebra to carry through, and I would recommend when you're doing problems like this, and I don't even know if you have one of these in the homework, maybe a simple version of this. Again, I've tried to keep this. Imagine putting some numbers into these formulas and actually starting to substitute numbers in earlier. I know this is one of those cases where even though I'm always saying try and do all the algebra first and then look at your formulas, and once you got the formulas then plug numbers in, this approach might work better if you start to put numbers in along the way, just because the algebra is so unwieldy. We need some wieldy algebra, not the unwieldy type. So anyway, these are the formulas, let me switch to these. These are the formulas that we've come up with. Now I've solved for I1, and then to solve for I2, I used an algebraic trick. I realized that 1 and 2, oh, here's the circuit right here. 1 and 2 are arbitrary. If I switch my 1s with my 2s, that would be this very same circuit. So I did that. I just labeled things differently in order to go in and get I2. Everywhere there was a 2, I put a 1. Everywhere there was a 1, I put a 2. And that's going to solve for I2. So these are my two formulas. Now what's nice about the algebra was miserable, I know. What's nice about the algebraic approach is now we can answer the question of, is it possible, are we guaranteed that the current 1 is going in this direction and current 2 is going here? Well, let's take a look and see. What my formulas tell me is my numerator will be positive if R2 plus R3 times V1 is bigger than R3 times V2. But if that's not the case, there is the possibility of, if V2 is really large, if V2 is significantly larger than V1, then V2 could actually drive current backwards through V1. Now, if these are ideal batteries where the chemical reaction can easily be reversed, then that would be recharging the battery. So again, if V2 is large enough that this I1 goes negative, what that's telling us is that V2 is driving the current backwards through V1. Similarly, if V1 is really big in this equation, then battery 1 could be driving current backwards through the other battery. Again, if the batteries are ideal, which means we can just reverse the chemical reactions that are taking place, then we'll be recharging that battery. We'll be replenishing the reagents that are being used in the chemical reaction for that battery. Okay, so that's the nice feature here, is we can figure out under what conditions I1 will be in the positive direction, negative direction, same thing for I2. So these are the rules that we followed. These are called Kirchhoff's rules, and boy, there's another example here. There's a number of these in here. I would stay with the easier ones on this. I'm not going to ask any super difficult loop. If I have any kind of loop set of equations like this on an exam, I would keep it very, very simple. Okay, something like, I'm going to say the example that we just went through is probably one of the easier examples. And let's go back and ask ourselves real quickly, why is it we had to use loops again? Why couldn't we just use series and parallel? And it's because nothing here is in series and nothing is in parallel. And you might say, well, aren't 1, 2, and 3 all in parallel? Well, they're drawn parallel. But remember, parallel says that there's two separate paths that I can take in getting back to the very same place. The presence of that battery prevents R2 and R3 from being in parallel. And the presence of the battery here also prevents R1 and R3 from being treated in. So there's nothing, I cannot use the approach of combining in series or combining in parallel in order to simplify this circuit, and that's why we're left with doing circuit loops in order to solve this problem. So I think that was traumatic. I think that's probably a good place to stop and take a break. Again, it's following Kirchhoff's rules. They have one more example here, but I'm not going to bother with that. Just looking ahead to see what we've got left. Okay, I think we're looking pretty good, actually. Okay, let's stop there. Take a break. If you guys have questions, let me know. Don't hesitate to stop by and ask questions during office hours.